Welcome all to the fourth seminar in this webinar series that we have been organizing under the umbrella of Geophysical Flows Lab, which is a research initiative recently started at IIT Madras. Today we have with us Professor Vamsi Chalamalla. He is currently an assistant professor in the Department of Applied Mechanics at IIT Delhi. Before joining as faculty at IIT Delhi, he was a postdoctoral fellow at the University of North Carolina, Chapel Hill, before which he did his PhD and MS in mechanical engineering at the University of California, San Diego, where he worked with Professor Sutanu Sarkar. His BTech studies in mechanical engineering was from IIT Guwahati. It's a pleasure to have Vamsi for today's webinar. Uh, we have worked with each other for quite a while now and had several interesting discussions. So, looking forward to his talk today. And today he'll be talking to us about internal waves in the upper ocean. Vamsi?
Yeah, thanks, Mani, for the introduction. And, good evening, everyone. Let me just turn off my video and then I'll turn it on at the end. All right, I hope you're able to see my screen.
Yeah, you could go to full screen.
Yes, yeah.
Yeah, perfect.
Okay. So, um so today I'm going to discuss about internal waves in the upper ocean. So primarily I'll discuss, so the first half is concerning the internal waves generated by the gravity current, and the second half is about near inertial waves. And so the first talk that I'm going to present is work done in collaboration with Tanmay Agrawal. He's a PhD student at IIT Delhi in our department. And the second part on near inertial waves is primarily done by Shiva. He is also my PhD student. As part of his thesis, he's been working on near inertial waves. So today I'll be talking about these two topics. But before going into the research talk, I'll just give a brief introduction about internal waves. I know some of you are already familiar with internal waves, but I'll just give a brief background. So internal waves are gravity waves which exist in the interior of the ocean. So you don't see like surface waves which propagate at the surface of the ocean. The internal waves exist and propagate in the interior of the ocean. And so the schematic here that you see on the right hand side nicely demonstrates it. But this is just a simplified version of the internal waves. But in reality, internal waves exist in the ocean in many different forms. Actually, you can see these solitary waves which are propagating at steep density gradient. We have vertically propagating waves, wave beams. So there are multiple forms, and so gravitational force is the restoring force for the internal waves. And when there is slow evolution of these waves, the Earth's rotation become important, and the Coriolis force will also contribute to the restoring force. So we call them inertial waves or near inertial waves. And I'm also showing here the dispersion relationship relating the frequency and the background stratification of these waves. So one of the interesting properties is that these are transverse waves. So the group velocity and the phase velocities are perpendicular to each other. And so the frequency of these waves will be within the range of F, which is the local Coriolis frequency, and N, which is the local buoyancy frequency, which is the property of the ambient. So as I've already mentioned, internal waves exist in different forms in the ocean. So today we are going to talk about internal waves excited by the propagating gravity current. So here I'm showing one of the observational study done near the Columbia River. So on the left hand side, you see this satellite picture where you have this river plume in the coastal ocean, and you have these waves which are propagating ahead of this plume. All right, and on the right hand side, so they have some ship based observations as well from this study. You can look it up in this paper for if you want to know more details about this. So on the right hand side, I'm showing the evolution of these solitary waves which are being released from the plume. So in the top panel, you can see there is a depression. So the black lines that you see are the isocontours of density. So see a depression which is formed just at the edge of the plume. So the blue colored fluid that you see here is the plume. So you see the depression which is forming just ahead of the plume. And then as the plume decelerates, so initially it has a velocity of the order of zero 0.6 meter per second. As the plume decelerates, you can see these internal solitary waves being released from the plume and then propagating ahead of it. So you can see this depression, which is, so the black line here, the solid black line that you see in the second row is the location of the plume. And you can see that this depression is propagating ahead of it. So the reason for this the free propagation of these waves is that as the plume decelerates, the wave speed, uh, which is basically the linear long wave speed, which can be defined using the ambient properties, nh divided by pi. So when the wave speed exceeds the plume speed, the waves will be released from the front, and we can see the free propagation in the third bottom panel. We can see the free propagation of these internal solitary waves. In fact, these observations have they have spotted these waves several kilometers ahead of the plume. I think 4 or 5 kilometers ahead of the plume. And if you look at the isopycnal displacement here, so they are of the order of 25 to 30 meters, which is actually comparable to the internal waves which are generated by tide topography interaction. So generally it is believed that internal waves in the ocean are primarily due to tide topography interaction. But here in this study, they also say that this is an important mechanism which has not been studied well so far, and which can be common phenomena at many locations, especially in the coastal ocean region where the river joins the coastal ocean. So this is from another observational study. It's a recent one. So they also have observed the solitary waves. You can see from the satellite image the wave train which is propagating ahead of this intrusion. So this is a measurement taken near Ford in Canada. So here in the top panel on the left side, you can see the wave. There is an intrusion of the fluid. So the difference between the previous observation and this one is that the fluid which is intruding is actually denser than the surface water. So it will actually intrude not at the surface, but somewhere in the intermediate level. So there is intrusion, and then you can also see the wave generation and propagation ahead of this plume. On the right hand side figure, you can see the solitary wave feature and amplitude of the order of 10 meters again. So which is again comparable with the waves formed due to tide and topography interaction, which is already well studied phenomena in the ocean. So what we did is we actually performed a laboratory scale computational study, numerical simulations, where we have varied several parameters. So I'll discuss in detail what are the parameters that we have varied. But here I'm showing the schematic of the computational study. So we have this current. Okay, so the density of this current is actually smaller than the density at the surface of the ambient. We have an ambient whose density is varying linearly. So it's increasing from rho naught to rho b from top to bottom. All right, and so the small h is the depth of the current, and capital H is the total depth of the fluid column. So we have actually performed both 2D and 3-dimensional simulations. So in 2D simulations, we will be just looking at one particular plane, whereas in the 3D, we have this width as well, finite width. And we have considered free slip boundary condition at the top and bottom surfaces. And the reason for this is we want to mimic the conditions relevant to the river plume, where when it is flowing at the top surface, it will be a free slip condition. And many of the previous studies, there are many laboratory and computational studies, as well as there are some theoretical studies which looked at this gravity current problem. but there are very few studies concerned about this partial depth. So typically they do lock exchange problem where this current fluid occupies the entire depth of the fluid column, right? And also, I think in experimental studies, it's easier to set up this current fluid at the bottom. So many of these experimental studies are bottom propagating gravity currents, whereas here we have considered the gravity current propagating at the top surface with a free slip boundary condition. Whereas in the uh, previous computational and laboratory studies, they have considered no slip boundary condition. We have actually observed significant difference in the front speed between these two boundary conditions. So I'll discuss that later. Uh, so the parameter space, actually this problem is very rich in parameter space. Uh, for example, some of the parameters that we have considered here is so the density difference between the current and the ambient. So if we call, so we're calling this density of the current as rho c. So rho naught minus rho c is the density difference at the top surface, the horizontal density difference at the top surface, which is actually driving this gravity current. And the other one is the density difference between the top and bottom surfaces of the ambient, which is rho b minus rho naught. And also, of course, we can also vary the depth of the current, small h, and the total depth of the ambient, capital H. So we can form some non-dimensional parameters from these, from these dimensional quantities. So a couple of them I'm showing here. So we define R, which is rho naught minus rho c, which signifies the horizontal density difference at the top surface, divided by rho b minus rho naught, which is the vertical density difference of the ambient. So basically, if we have considered wide range of parameters, wide range of values for R, ranging from much smaller than 1 and I think of the order of 100 also, we have considered R of the order of 100. So basically what it signifies is for large values of R, so which means the density difference at the surface, the horizontal density difference at the surface is much, much greater compared to the density difference, the vertical density difference in the ambient. Whereas in the other case where R is much smaller than 1, so which means it's a strongly stratified medium, high stratified medium. So rho b minus rho naught will be much, much greater compared to rho naught minus rho c. So the other parameter is h, small h divided by capital H, which we are calling it as depth ratio. So we varied this parameter as well. We have considered 3 or 4 different values for this. And of course, there is one more parameter, which is Rossby number. But in this study, we are not considering background rotation. So we don't have any Rossby number for this study. So coming to the simulation parameters, so I'm showing the table, various simulations that we have performed so far. Also, I just want to mention, if you have any question at any point, you can stop me in the middle. So I'll be happy to discuss. Yeah, so we have performed multiple simulations varying the depth ratio, small h by capital H, and we have also varied the background stratification N. So we have considered unstratified case, and we have also considered as strongly stratified case. So basically, the R is the parameter which, as I've mentioned, R is the ratio of density difference at the top surface divided by the vertical density difference of the ambient. So large values of R signify that the density difference at the top is very large when compared to the ambient density gradient. So in this case, the flow will be supercritical. So when I say supercritical, it is governed by a non-dimensional parameter called a Froude number, which I'm showing here. So Froude number is the ratio of U, which is the front speed, and NH. N is the ambient buoyancy frequency, and capital H is the total depth of the fluid. In fact, this comes from the fact that the long wave speed of the ambient can be defined by NH divided by pi. So if we define Froude number as U divided by NH, so Froude number less than pi, 1 by pi, we call it subcritical, where the where the front speed is smaller compared to the wave speed. And in the case of supercritical, the front speed is greater than the wave speed, long wave speed. So if you look at the right column here, actually, so the Froude number we have considered, depending on the values of R, we have obtained wide range of values for the Froude number as well. So which is 2.79, which is supercritical, of course, and 0.09, which is subcritical. And we have also varied uh, the total depth of the fluid column as well in some cases. And we have performed some 3D simulations apart from the two-dimensional simulations. So primarily, we also wanted to look at what is the difference between 2D and 3D simulations. Qualitatively, do we get similar features? And also, we want to look at the turbulent statistics, whether it is shear driven or whether buoyancy becomes important at some point. Uh, yeah. So I'll be showing some animations. So here I'm showing the density field for that we have obtained from 2D simulations. One is for the supercritical case where Froude number is much greater than 1 by pi, and the other one is subcritical where the Froude number is less than 1 by pi. So you can see here for the supercritical case, the flow is dominated by shear instabilities. You can see this Kelvin-Helmholtz billows rolling up the density field. There's mixing going on. And at the same time, we can see this in solitary wave feature, these isopycnal displacements. Uh, and this solitary wave is actually locked with the front. So it's not propagating ahead of the front, but it is, you can see it is observed just ahead of the plume, and it is propagating with the plume. So you can say it is locked with the plume because the front speed is actually greater than the wave speed in this case. Whereas in the case of subcritical, so the bottom panel shows the subcritical case. So you can think of this as a highly stratified medium. So for a highly stratified medium, the Froude number will be below critical value. And so you can see the evolution is significantly different when compared with the supercritical case. So here the solitary wave feature is not very prominent. Rather, what we see here is the internal wave modes which are propagating into the interior, and there are multiple modes, formation of multiple modes, which are propagating in either direction. Whereas here we don't see, the vertical propagation of these waves. Primarily, we do see this depression which is forming and which is moving with the plume. And we can also see that so the mixing is, so let me play this supercritical case again. We can see this rolling up and mixing of this density field, which is not very prominent in the case of subcritical, because we can expect that because the front speed is also smaller when compared to the supercritical case. So the shear itself is decreasing. So in the subcritical case, we do see some isopycnal breaking density mixing, but not as prominent as in the supercritical case. You can see this different mode. I mean, I'll show it again in the next slide where we look at the velocity field. You can see the different modes, formation of different modes, and which are proper the interior. Uh,
Vamsi, since you said you are happy to take questions, there is a question in the chat box.
yeah, sure.
If you don't mind.
Yes, yes. Yeah. Let me. Criteria behind constant HL and Okay, actually, we haven't considered a constant edge. We have, in fact, varied the depth of the water column as well. I'll show in the further simulations. And regarding the L, I think L, you're talking about the length of this lock. So from previous studies, we have found that the length of this lock actually does not have any significant impact on the dynamics. So that is why we did not consider varying this length of the lock. All right, I hope that answers the question.
Sir, if you don't mind my asking a question,
Yes, yeah.
Professor Vamsi, yeah. So the top surface is the the surface is fixed, is it? That is, there are no. It's not a free surface.
No, no, it's not a free surface. It's
It's
just
not
a
a free
free slip
surface.
boundary condition. Yeah, it's not
I
a free
see.
surface.
Okay, right. Okay, thank you.
Yeah, it's a rigid lid boundary condition actually. So W is zero at the top surface.
Right, because it looks like the supercritical one would actually perturb the top surface otherwise,
Yes,
isn't
yes,
it?
definitely. Yeah.
Okay, thank you very much.
Yeah, we don't have that feature yet in a solver, so we didn't include it yet. Yeah. All right. So coming to the, so I'm showing the velocity, streamwise velocity animations now for the same cases as I've showed before. So the top one is again the supercritical case. You can see this strong current and the solitary wave feature which is propagating with the front. So there is no wave propagation ahead of the front here in this case, whereas we can see some waves propagation in the other direction. Whereas in the case of subcritical, if you look at the subcritical case here, so the dynamics is significantly different. So here we will see formation of uh, multiple modes, internal modes, and there is propagation into the interior as well.
Vamsi, if you don't mind, you could go to full screen mode. Thank you.
Yeah. So here we can see this mode one wave, which is propagating actually ahead of the front. Since this the wave speed, mode one wave speed is greater than the front speed, so it's detached from the front and it is propagating ahead of it. And we can see the formation of mode two wave behind it. So there is a train of mode one waves which have been released from the front, and then behind it we can see mode two wave forming at the front. So this is a significant difference between the supercritical case and the subcritical case. So in the case of supercritical Froude number, we have this solitary wave feature which is locked and moving with the front. Whereas as we go towards subcritical regime, we see, we don't see this prominent solitary wave feature. Rather, what we see is these multiple modes, formation of multiple modes and propagation into the interior. So here I'm just summarizing it. So this is again from the 2D simulation, the density field. Uh, so as we go from top to bottom, so the R is decreasing, so which means the stratification. So this rho B minus rho naught is much larger compared to rho naught minus rho C. So in other words, you can also think of it as increasing stratification. So with increasing stratification, you can see the solitary wave feature is disappearing, and then we see propagation, we see formation of these multiple mode wave modes. And other interesting feature we see in the middle panel. I think this is somewhere closer to critical. I'm not sure exactly what is the Froude number in this case. So here actually we can see this solitary waves detaching from the front. So this is the front location. So the solitary waves detaching from the front and moving ahead of it. So here as well in the bottom panel as well, we do see some solitary wave kind of depression, but it's actually not very clear because it's not evidently seen, at least from the isopicnals, it's not very clear. Whereas from the velocity field, if you look at the velocity field here, so this is the velocity field, streamwise velocity field. Again, so from top to bottom, it is decreasing R, so which means increasing stratification. So Yeah, we can see here in the bottom panel, we can see formation of mode 1 wave, which has detached from the front and moved further, much farther ahead. And even, in fact, mode 2 wave also have detached from the front. And behind it, we can see the formation of mode 3 wave.
Can I ask a question, Vamsi?
Yeah, funny.
In the case where you're seeing these different modes, what is the frequency associated with those modes?
Uh, we didn't actually check the frequency,
Okay.
but
So
yeah,
you could take the horizontal wavelength that you see in these modes and use the dispersion relation to.
right. Yeah, we should be able to get it.
Uh,
Right. Yeah,
so
we
I'm
didn't.
just wondering what is the mechanism that behind the frequency selection of these internal waves.
Right. Yeah, it's an interesting question.
Uh,
Yeah, we will look at it, but yeah, I think it's a good thing to explore.
and a second question, when you say solitary waves, why do you call them solitary waves?
So, I mean, if you look at it from so this is a depression feature which is typical of solitary waves,
Okay.
and is formed due to nonlinear effects. So there is a transition from supercritical to subcritical. Like behind the plume, it is supercritical, and ahead of the plume, it's subcritical. So there is like a hydraulic jump. It's like hydraulic jump, which is typical condition for formation of solitary wave.
Okay. Thanks, Vamsi.
So here I'm showing a density field for from two-dimensional simulation again, but for a different depth ratio, h by h of 1/3. In the previous case, it was 1/6, h by h of 1/6, and now it is 1/3. So what we observe is this isopycnal displacement in the supercritical case increases. So this amplitude of this displacement increases, and also in I mean, I'm not showing the velocity field here, but even the amplitude, internal wave amplitudes also increases in even in the case of subcritical case. And in the bottom panel, in the middle panel, again we can see the detachment of the solitary wave. In fact, there are a couple of solitary waves which are detached from the front, which is located here, and propagating ahead of it. So there's more. I mean, if you compare this plot, if you look at just the top panel of this one and this one, so we can see there's more. Seems there's more mixing, and at the same time, the isobictal displacement, the amplitudes of this displacement is larger, just because of the fact that we have the depth of the current has been increased. So it's basically, you can think of it as a higher Reynolds number flow when compared to the previous one. But qualitatively, the flow looks similar. So we have this solitary wave feature in the supercritical regime, and these higher mode waves and the subcritical regime. So qualitatively, there's no difference when we change the depth ratio, but of course, there's more. The internal wave displacement, isopycnal displacement is higher, and there's more mixing. We also performed, as I said, we have also performed some three-dimensional simulations. So this is for the depth ratio of 1/4, and this is again for the supercritical regime. So you can see this roll-up shear instabilities and the mixing of the density field. So we do see a solitary wave-like feature which is propagating ahead of the plume, but the structure is actually not as coherent as we see in the 2D, because there is since it involves the third dimension, there is more these vortices break up and there's more mixing. So we don't see a clear coherent structure for the solitary wave, but we do see you can see here a similar feature is propagating with the front. All right. So I mean, here I just want to show the velocity field from three-dimensional simulations, how they are qualitatively different. Also, I just want to showcase this cool feature of this computational solver, where we have this gray color that you see, gray shaded region that you see is the refined mesh. So this solver can dynamically refine the mesh along in the regions of turbulence. I mean, when I say regions of turbulence, we do specify based on what criteria the grid refinement has to be done. So here we have specified that if a density difference between the adjacent cells is greater than a particular threshold value, so it will refine that particular grid. So you can see that, so as the plume is propagating, you can see this fine level mesh, this gray shaded region also is evolving with the plume.
Sir, so you had this fine mesh even in the 2D simulation, this adaptive part?
We do have it. Yeah.
No, I was just curious because here the flow features seem to have much more smaller scales, no, finer.
Right. Actually, the grid resolution is also slightly different between 2D and 3D cases.
I see. Okay. Yeah. Oh, for computational reasons. Okay.
Right.
Thank you. But this does show finer scales, isn't it?
Right. Yeah. So in fact, we have, so we wanted to look at the turbulent kinetic energy budget in 3D cases. So that's why we have actually, taken finer mesh in the case of 3D, especially in the vertical. So again, from the subcritical case, we can see the evolution. So in the supercritical case, we see this strong jet or plume, which is propagating ahead. Whereas in the case of subcritical, we can see the vertical propagation of waves. Here, in fact, you can see this mode 1 wave being released, detached from the front and moving ahead of it. And there's mode 2 wave, which is formed behind it. So yeah, somebody was asking, we did vary the total fluid depth. I just wanted to highlight the difference here. So on the left side, the animation is for h by h of 1/4, and on the right hand side, we have increased the depth, total depth. So in the left side, we have 40 meters, and on the right hand side, we have 80-meter depth. So qualitatively, the difference, so when you increase the depth, the fluid column depth, the long wave speed increases because it is proportional to h, and h divided by pi. So primarily, the difference is that the waves propagate ahead of the front, which we don't see in the left-hand side panel. So we can see on the right-hand side the mode 1 wave, which is actually propagating well ahead of the front, and we can see the formation of mode 2 wave as well. So we wanted to quantify the Froude number. So as we have defined Froude number, it's a ratio of U and NH. So we wanted to see how they vary with R. So some of the previous studies have in fact reported that Froude number varies as logarithmic function of R. So here we wanted to see, of course, the boundary condition is also different in our case. So here we wanted to see how the Froude number varies as R. So on the left-hand side panel, we are plotting the Froude number versus R for two different depth ratios. So the red color shows for 1/3, and the blue color is for 1/6 depth. So this is from the 2D simulations. So we do see that, so it's not logarithmic for the entire parameter space here. So it's varying as logarithmic function only in a small range of R. Rather, it is Froude number is varying as some power of R, which is R to the power of half in this case. But again, it is depth dependent. So for h by h of 1/6 and 1/3, we get different evolution, but both are following the same power law, R to the power of half, but the coefficient is different. So we have 0.3 for depth ratio of 1/6 and 0.42 for the depth ratio of 1/3. So we thought, like, why don't we plot Froude number as a function of h by h, and we have taken the product of h by h and R. And interestingly, what we see is that all these data points fall into the same curve. In fact, even the 3D cases are agreeing well with this scaling, except for, you see some green square, which is actually the data points for full depth block, where h by h is 1. where the current occupies the entire depth. So you see slight deviation for the full depth lock, but for all the other partial depth cases, we actually see nice agreement with this scaling. Also, we wanted to understand in terms of the potential energy available in the system. So initially, since you have lighter fluid on one side and denser fluid on the other side, so there is some potential energy which is trapped in it. So we wanted to understand in terms of potential energy how the fluid number varies as potential energy itself. So we define the available potential energy. Of course, this is not the traditional definition that oceanographers use. This is a slightly different definition of available potential energy. So where we have rho c minus rho of z. So where rho of z is the density of the ambient, since it is varying in the vertical direction. And we integrate over that from minus h to 0, which is the log depth. So interestingly, what we see is that even though the available potential energy increases, the fluid number decreases. I mean, one would expect that as the available potential energy increases, you can see that the front, the kinetic energy would be larger, and the front speed would be higher. But what we see here is even when the available potential energy is increasing, the fluid number is actually decreasing. So then we realize that maybe it's because the stratification is also playing a role here. So we should look at the normalized value of the available potential energy. So we are normalizing with the factor of n square and h cube, where h is the depth of the current and n is the buoyancy frequency of the ambient. So what we see is that, so the plot that I'm showing here is fluid number versus normalized available potential energy. So we indeed see that fluid number is monotonically increasing function as a when we plot with normalized available potential energy. Of course, there is difference coefficient. So for higher depth ratio, for h by h of 1, for the same value of normalized AP, we get higher fluid number. And similarly, so the fluid number is basically dependent on both depth ratio as well as the normalized available potential energy. Of course, on the x-axis, if we plot maybe a product of h by h and normalized APE, probably I guess they may fall into a single curve, but we didn't check it yet. So as I said, so we also looked at the turbulent kinetic energy evolution for different cases. Yeah, actually, it has to be decreasing fluid number, not increasing fluid number. So this is the supercritical case, the one on the left-hand side. The equation that I'm showing here is the evolution for turbulent kinetic energy. So we have multiple terms here. So this is the transport term, and you have the shear production, and this is buoyancy production, and finally the last term is the dissipation rate. We just wanted to quantify, what is the dominant source of turbulence here, and what we found is that it's primarily shear driven. So the shear production is balanced by the turbulent dissipation rate, whereas the buoyancy production and the transient term, the d by dt of turbulent kinetic energy, so they are small when compared to the other dominant terms. The shear production, the red curve here is the shear production, and the magenta color is the dissipation rate. So primarily the balance is between these two, and that is consistent among all the all the cases, whether supercritical or subcritical. And another interesting thing that we observed here is that there is a decay of turbulence, and then we do see a resurgence of the turbulence again at some point. So in the first figure on the left hand side, you see there is a decay until 300 seconds, and then there is again a resurgence, and which is continuing. So we see that trend in all the cases, but that time is different though. So with decreasing, so the right hand side is the lowest fluid number, and the left hand side is the highest fluid number. As we go towards the lower fluid number, we do see actually there is minimum levels of turbulence, and then we do see a resurgence of these turbulence levels again. So we don't know yet what is causing it. We need to look at it probably in more detail. So in summary, so we have observed strong shear instabilities and KH belows for supercritical case, that is for lower stratification, and we do see solitary wave feature for near critical and supercritical cases. Whereas as we move towards subcritical regime, we do see vertical propagation of internal waves, and of course we don't prominently see these shear instabilities or KH belows. And we also quantified the Froude number, and we see that it's varying as r to the power of half for all the cases. And also we found that it is dependent on depth ratio. Uh, and when we looked at the turbulent statistics, we found it's primarily driven by shear production, which is balanced by the dissipation rate. Of course, so there are uh, many more things. As I said, this is a problem with rich parameter space. So there is a large scope of looking at other parameters. For example, we didn't include the mix layer in the ambient. So in the ambient, we just considered linear density variation from the top surface. But in reality, there will be mixed layer in the ambient. So it would be interesting to see what would happen if we include the mixed layer in the top few meters of the ambient. And also, we didn't include any rotational effects here. So that would also be interesting to see. And so we also think this particular phenomena will be very relevant to Bay of Bengal because there is strong river input and there is large variation of stratification, seasonal variation of stratification as well. So the conditions can be favorable for both supercritical as well as subcritical regime. But we haven't come across any observational data yet reporting the formation of these waves, either satellite pictures or the in situ measurements. But if any of you are aware of it and if you are interested, then I'd be happy to talk and collaborate. Yeah. So this ends the first part of my talk. So if there are any questions, I'll take before moving on.
Sir, I have a question.
Yeah.
Sir, about H by H. So when I think about it, like it's like a small H by H is like zooming out of the whole picture, right? So do you think that at very small H by H, the dependence on F Froude and H by H would be minimal, and at large H by H, maybe the because of the boundary conditions, there's a dependence on Froude.
Um, okay. So from what I understand, so you're saying so if we consider very small values of H by H, would that scaling it still would it
Does
still
it like does it come to like does the dependence on H by H decrease for very small H by H?
right? So when we consider very small H by H, uh, well, of course, so since this is free sleep boundary condition,
Mm-hmm.
um, yeah, and also when we compare it with the full depth cases, as we have seen, actually for the full depth cases, the scaling there is deviation from the scaling, probably because this scaling is coming from the fact that Froude number is proportional to, or U is proportional to square root of GH, is coming from actually the shallow water theory, which may not be valid for full depth cases. Whereas for the case where uh, your plume is H by H is very small, I think, I guess, I don't know, but I guess this scaling would still be valid.
Okay, sir. Thank you.
Yeah, Vamsi, I have a basic question.
Yeah,
So your fruit number is defined as U by NH, right?
right.
That U is something that you impose or that is something that is
No.
chosen by the flow?
So U is basically the front speed that we measure from the simulations.
I see. So you don't know a priori if you're doing a subcritical or a supercritical case.
No. Okay. We don't know that. It appeared as if I think in the table I've shown the Froude number, but yeah, apparently we don't know.
Oh, I see. But there should be some scaling loss for the front speed, or
So for uh, full log depth, I think there are scaling which is available where U is proportional to G prime H.
okay,
So yeah, so based on that, we can get some idea about the Froude number of the flow.
I
Uh,
see. Thank you.
So how much time do we have left?
Uh, 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 Maybe 10-15 more minutes. Is that fine?
Yeah. So I'll briefly go over it. I mean, I'll not go into the details, but I'll just briefly.
Perfect. There may even be questions on your first part itself. So,
Yes, yes. If there are any further questions, I can answer
yeah,
now.
yeah. Please go ahead, Vamsi. Thank you.
All right. So yeah, so this work is primarily done by, as I mentioned before, by Shiva. I think he's already here. So this is part of his PhD thesis work. So here we looked at the near inertial waves, as I've already mentioned in my first slide. So internal waves exist in the ocean in many forms. So near inertial waves is one of it. Where so we call it near inertial because the frequency of these waves are closer to the inertial frequency f. All right, and so some of the previous studies have also reported that when they look at the spectrum, the frequency spectrum in the ocean, so they actually see a dominant peak at f. So uh, and they're primarily excited by storms, and the picture that I'm showing here on the right hand side is genesis and track of multiple storms between 1972 and 2017. So the motivation behind showing this picture is that storms are very common in the Bay of Bengal region, and because of that, the near inertial oscillations or near inertial waves are found to be very prominently seen in the Bay of Bengal region. So the time evolution of these waves are slow, such that the Earth's rotation is actually playing an important role in these waves. And so there is a review paper by Matthew Alford, so where they have nicely described different generation mechanisms of near inertial waves, their characteristics, and also decay mechanisms associated with them. So what they say is that these near inertial waves are actually very important contributors to the upper ocean mixing. So they could play an important role even in the SST, sea surface temperature, and the mixed layer depth. But I mean, now I think at this point the generation mechanism of these near inertial waves are more or less understood. But what happens to this energy as it propagates into the interior, and what are the decay mechanisms is still not clear. And of course, we have to know how this energy decay happens, and before we actually parameterize, or before we include the role of near inertial waves in the global ocean models. So what we do here is, so we perform some large scale simulations using ROMS, regional ocean modeling software. So this setup is actually motivated by one of the previous theoretical study by Moelis and Smith. So I'll briefly explain the computational setup, and then I'll show some results. And I'll just go to summary. I won't go into the details because we are running out of time. So this is the 3D computational box. So what we have here is that initially we initialize the simulation with zonal velocity. So zonal direction is X. So you can see the axis system here. So Y direction is where the Coriolis force is varying. So we are considering a beta plane approximation where the Coriolis force is varying as beta Y. So it's varying, the Coriolis force is varying with Y in this direction. And we have an initial velocity in the zonal direction, which is u of y. It's not a constant along the y direction. So we give some, I think, Gaussian profile of y, u of y. And we have periodic boundary conditions in the horizontal direction and free slip at the top, and uh, quadratic bottom drag, I think, yeah, at the bottom boundary. So as far as the density field is concerned, we have mixed layer in the top 30 meter. So you can see in the right hand side figure. So we have mixed layer in the top 30 meter, and then the density is increasing linearly with depth. So initially the velocity is, the u that I'm showing here is has a finite value in the mixed layer, and it is 0 below the mixed layer. So we initialize it with zonal velocity, and we have beta effect, and we want to see how is the evolution of this flow field. So the length scales here are 1000 kilometers in the meridional direction, and 500 kilometers in the zonal direction, and 2 kilometers in the vertical direction. I think the grid resolution are of the order of 2 kilometers in the horizontal, and in the vertical it varies. At the top surface we use stretch grid, so at the top surface it's of the order of a meter, I think, and then it increases as you go deeper. So here I'm showing an animation of meridional velocity field on a YZ plane for one particular stratification value. So we can see, there are two important observations here. So one is that we can see the reduction of these length scales as already predicted by previous theoretical studies. And then there is vertical propagation of these waves into the interior. So the wave number actually increases as beta t. So it's already discussed in this paper by Eric Desaro. So he has extensively studied this problem. There are multiple publications on this. So I'm not going into the details, but so there's already some theoretical understanding of these waves. But what we wanted to look at is, so if we consider nonlinear effects using these 3D simulations, would it be any different from the theoretical estimates of as reported by previous researchers? And the other interesting thing here is that we do see only southward propagation of waves, because these, as I mentioned before, these waves have frequency of local Coriolis frequency, local inertial frequency f0. So they cannot propagate towards higher latitudes because the frequency of these waves are smaller than the local Coriolis frequencies at higher latitudes. So they can only propagate southward. Whereas if you have formation of higher frequencies, for example, super harmonic frequencies, they can propagate towards the higher latitudes. So we looked at what is the effect of varying stratification. So we have a mixed layer in the top 30 meter, and then the density varies linearly. So that linear variation in density can be characterized by n, which is n square is proportional to the vertical density gradient. So we varied this value of n, and we see how the the waves, qualitatively, how are they different when compared for different stratifications. So as you can see here in the top panel is unstratified case, n is 0, and so as you go towards the bottom panel, the n is increasing. So what we see here is, when we increase the stratification, primarily we see formation of higher modes, higher vertical modes. And so these also, the waves are becoming shallower. So as you can see here in the bottom panel, so I'm showing the direction of the group velocity as well as the phase velocity. So there is reduction of vertical scale as stratification increases. So that is the primary observation that we have. And when we looked at the frequency spectrum, so interestingly, what we see is that when we look at N0, which is unstratified case, we do see a peak at the local Coriolis frequency. Of course, so this is f by f0 is 0.9, because this FFT we have taken at Ly by 4, where f0 is local Coriolis frequency at Ly by 2. So what we see is, as the stratification increases, so the contribution of the 2f0 frequency increases. You can see for N2 we see a smaller peak, whereas if you go to N5 is the highest stratification that we have considered, which is 0.005 per second, I think. So at the highest stratification, we see that the 2f0 frequency is becoming prominent. So one of the reasons that we think the 2f0 is becoming prominent is because of the nonlinear interactions among different modes of these inertial waves, which is leading to the formation of 2f0 waves. So there are multiple publications from Professor Mani's group on this topic, actually the modal interactions leading to higher harmonics. So I think that is the reason here, that as we increase the stratification because of this higher vertical modes, we do see formation of higher frequencies as well. We also looked at the modal decomposition, like what is the contribution of each vertical mode in the velocity field. So one observation is that as we go, so on the y-axis we are plotting the modal amplitudes, on the x-axis is the mode numbers. So as we go towards higher stratification, what we see is that the contribution of higher modes is increasing, as we have already seen. And similarly, for the double inertial frequency, we do see a similar trend that the contribution from the higher vertical modes is increasing at higher stratifications. And we also looked at how the mixed layer kinetic energy is evolving with time for different values of stratification. So what we see is that as the stratification is increasing, the kinetic energy decay rate is also increasing. And to understand that, we have actually quantified the wave flux at the base of the mixed layer, which I'm showing on the right hand side plot. So the vertical flux at the base of the mixed layer is increasing as the stratification is increasing, which is actually the reason for the decay in the mixed layer energy. Of course, there is also a small fraction of dissipation which is going on, but I think it's a very small fraction when compared to the energy flux at the base of the mixed layer. We also looked at the effect of initial velocity, varying the amplitude of the initial velocity. In the previous slides that I have showed you, the velocity amplitude was 0.1 meter per second. And in this case, we have considered amplitude of 0.3 meter per second. And we have looked at the frequency spectra at multiple locations and at multiple depths. You can see the y is equal to Ly by 4, Ly by 2, and 3Ly by 4. And we also looked at multiple depths. So what we see is that as we go towards higher depths, then we can see a shift in the frequency peak from, so in the first, actually it's not very obvious here, but the first peak here is at 0.9, whereas in the bottom panel, left hand side bottom panel, the peak is observed at f0. So the reason we think the peak is shifting is because there is contribution from waves which are formed at the higher latitudes and which are traveling towards the lower latitudes, which is contributing to the frequency spectra at Ly by 4. And we have also considered the frequencies FFT at 3Ly by 4, where our forcing is actually not given. So our forcing is only restricted between, I think, Ly, it's not extended until 3Ly by 4. So that's why we don't see any signal at f0. Rather, what we see is a peak at 2f0. And so the reason, as I said before, 2f0 waves can propagate to higher latitudes, which is, I think, contributing to the frequency spectrum 3Ly by 4. So overall, what we see is that when we increase the initial velocity amplitude, so the decay rate is also increasing. The decay rate of the mixed layer kinetic energy is also increasing. At lower amplitudes, the decay rate, the HK evolution with time is agreeing with one of the previous theoretical studies. But as we increase the velocity amplitude, it's deviating from the theoretical estimate. So one reason could be that at higher amplitudes, there is more dissipation because there is higher shear. So there's more dissipation, which is contributing to the energy decay here. Yeah, so I'll just briefly go through this slide. So we looked at the gradient Richardson number as well. So we found that as we increase the initial velocity amplitude, the region where the gradient Richardson number is falling below quarter is also increasing as expected, because as we increase the velocity amplitude, the shear increases. So, I mean, if we have enough vertical resolution, we can actually, we should be able to resolve these shear instabilities associated with near inertial waves. In this case, I mean, it's out of scope for this study, but we are considering another high resolution study where we can resolve these vertical scales, and we should be able to capture these shear instabilities and mixing at the base of the mixed layer. So the conditions, so this plot tells us that the conditions are suitable for wave breaking and mixing, but our simulations do not capture that here. Also, we looked at the role of eddy viscosity. We considered multiple values for viscosity in our simulations. So what we found is that the horizontal kinetic energy evolution is actually very sensitive to the viscosity that we consider. So that's why one has to be very careful when studying near inertial waves and their energy decay using these global ocean models. So in fact, the KPP, if you use KPP parameterization, the decay rate is actually significantly different when compared to the constant eddy viscosity models. All right, so this is just a summary slide. I'll just leave it for you to read. Yeah, so that's all from my side. If there are any questions, I'll take. Thank you.
Thanks a lot, Vamsi. That was very interesting. So there's one question on the chat box on the previous part, Vamsi, and then maybe we can invite
Yeah.
people to ask questions on the second part as well.
Okay. So Dheeraj, can the time instant where you see the decrease in decay related to time required for formation of solitary waves? No, in fact, solitary waves we do see from the beginning. Actually, we don't. I mean, as soon as the plume starts evolving, of course, it will take some time, but the time at which we see a decay in turbulence is not matching with the time that we see the formation of solitary waves. I think there
Okay,
are
the
other
floor is
questions.
open for more questions if there are any from the audience.
Hello, sir.
Yeah, hi.
Hi, sir. In the first problem regarding the 2D simulation, sir, is the current that is considered a constant flux one or a constant volume? It looks like a constant volume one.
Uh, yes, it's a constant volume one actually.
But in the first,
We have a sponge boundary condition at the left and right boundaries.
sorry, sir.
We have a sponge boundary conditions at the left and right boundaries.
Okay.
So, yeah. Sorry, you were asking something else.
Yes, in the first image of a river that we have shown there, it can be a constant flux condition at the entry of at the mouth of that river.
Right.
So, can the same thing be applied there in that
I think if we
situation?
take periodic boundary conditions, at
Yes.
least the left boundary, we should be able to impose that constant flux. But yeah, currently we're not doing that here because we have waves propagating in either directions. So if we take periodic boundary conditions, actually it would corrupt our computational domain. So that's why we did not take that. Instead, we have considered a sponge boundary condition where the waves will be absorbed as it reaches the boundary. But we can
Okay.
consider that.
Thank you.
Are there other questions?
Uh, Hi, sir. Regarding this near inertial waves,
Yes.
did you include any background flow in the models, in the
No,
ROMs?
there's no background flow. Just we initialized it with zonal velocity and then that's all. We have this beta effect.
Okay.
Any other questions? Yeah, Vamsi, I had one question from your first part.
Yeah, sure.
Yeah, there are these papers that talk about internal wave generation by turbulence or by gravity currents. I don't know if there is a difference. Is this related to the internal waves you see in the subcritical case? Are they related to
So
some
we,
papers? I can share them with you later,
yeah,
which talk about internal waves generated by turbulence in the mixed layer.
okay. I mean the small. So do they have like some kind of initial turbulence levels? Like do they initialize the flow with some turbulence, or is the
Yes.
turbulence created by the mean flow?
No, I'm not. I don't remember the details. I think it
Okay,
was more of an experimental work, or
okay.
How they generated the turbulence is not, I don't recall. But they
Okay.
do talk about, the interesting thing there is that turbulence contains energy across a spectrum of frequencies.
Right.
But there are specific frequencies that seem to be chosen by the internal waves. So, which is also why I
Oh, okay.
asked you the question
Yes,
on what
yes.
are these
Yeah.
frequencies associated with these internal waves you are saying.
Right, right, right. Yeah.
So it could be
So
interesting.
it's probably something to do with the background stratification, I guess, the frequency selection.
Uh huh.
So that is the time scale that we are imposing.
Uh huh.
But again, I think we can also have one more time scale based on density gradients and depth. Yeah, let me
Yeah.
take a look.
Yeah. It could be interesting to look at the frequency selection there.
Selection, yeah, yeah.
Yeah. Are there other questions? Okay. If there are no other questions, I would like to thank Vamsi once again. Thanks for accepting this invitation and giving this very interesting talk. I'm sure if there are any further questions from the audience, Vamsi will be willing to answer by email if you choose to contact him. Thanks a lot, Vamsi.
Thanks, Mani, for inviting me, and thanks everyone for attending the talk.
Thank you.